Okay, now we're going to look at if you're given a set of vectors, how can you decide if those vectors constitute a vector space? You know, a set can be any collection of vectors, but a vector space has to satisfy these rules up here. It has to be closed under addition, it has to be closed under scalar multiplication. So let's look at this. If we want to show that V is a vector space, then you have to show that it's closed under vector addition and show that it's closed under scalar multiplication. You got to show both of those. If you want to show that it's not a vector space, then you can get away with only doing one of the following. You can either find two vectors in the space in the set whose sum is not still in the set, or in other words, show that it's not closed under addition. You can find a vector v, little v and v, and a scalar for which c times v is not in the set. So that would be showing that it's not closed under scalar multiplication. Or you can do this last thing, show that v does not contain the zero vector. Turns out that's enough to show that the set is not a vector space. Now, notice there's no analog of that one up here. It's quite possible to have a set of vectors that contains the zero vector but still isn't a vector space. So what I want to do here is go through a bunch of examples and talk about whether or not the vectors that we're looking at, these sets, whether or not they constitute a vector space. So some of these we're going to do algebraically, some we're going to do geometrically, but let's just start looking at them. Okay, this first thing says the set of vectors in the first quadrant of the xy plane. Okay, so I'm going to draw the plane here. If we look at vectors that are in the xy plane, that's going to be in the first quadrant. That's going to be stuff that goes, out here. All these guys, they start at the origin and go in that direction. In short, you get everything over here. So, this is not a vector space, and here's the reason why. It's not closed under scalar multiplication. The reason is, if you take any one of these vectors over here and multiply it by a negative scalar, if you call that v, and this is cv where c is negative, then that's going to point outside. So I guess what I would say is if v is in this set and c is negative, then c little v is not in quadrant 1. And maybe instead of calling it v up here, maybe I should say if v is in quadrant 1 and c is negative, then cv is not going to be in quadrant 1. So this is not a vector space. All right, well, let's look at this next one. The set of all vectors that lie on the line y equals x. So here is our, so here's the line y equals x. If we start looking at vectors that lie on this, we're going to get all of these kinds of looking things. Some pointing in the reverse direction. And if you look at that, you can look at it and see that if you take any one of these and multiply it by a number, it's going to stay on the line. Even if it reverses direction, it's going to stay on the line. So it's closed under scalar multiplication. Also, if you add something on here onto another vector, it's still on the line. So the answer here is yes. This is a vector space. Okay, what about these? The set of vectors that lie on either the x-axis or the y-axis. So that's going to be vectors like this, or like this. Now, if you look at this, these are closed under multiplication, it looks like. Because if you take any of these guys and you multiply them by a number, it's just going to stretch or shrink it, and it might change the direction. So if you start with a vector on the x-axis, a multiple of it's going to stay on the x-axis. And ditto for the y-axis. But addition is going to be problematic here. Because if you add one of these vectors to one of these, you're going to get something that sticks off over here. So if this is u and this is v, then u plus v is going to come up here. So this is not a vector space. Because it's not closed under addition. All right, what about this next one? The set of vectors of the form xy where x is greater than or equal to y. Okay, so the first thing I need to do is just kind of plot this inequality. If you try to plot, let's see, I'm going to turn it around. Y is less than or equal to x. So that means I can plot y equals x here. And if y is less than or equal to x, that's going to be stuff that's below there. So that's going to be all of this part of the plane down here. So vectors in here, it could be anything that lies on this line or anything that points into this half of the plane. I drew those a little sloppily, but they're all supposed to be starting at the origin. So this thing, can we find something here that if we multiply it by a negative, it'll go out of there? Sure. Anything except for the ones that lie right on this line. If we take any vector that points into here and multiply it by a negative constant, it's going to point out of there. So this thing is not closed under vector addition. Actually, what I just showed was that it's not closed under scalar multiplication. Is it closed under vector addition? Yeah, I guess it is, because if you take any of these things, they're all going to lie under here. So I believe if you take any two vectors that lie in here and you add them together, it would be closed under addition. But it's not closed under scalar multiplication, therefore it's not a vector space. All right, what about this next one? The set of points on the graph y equals cosine x. So cosine x looks like this. So if we're thinking of these in terms of vectors, it would be little arrows that point from the origin to all of these things. It's much more convenient just to look at the points instead of drawing all these arrows. But is this a vector space? This one we can answer very quickly and say, no, this is not a vector space. And that's because it doesn't contain the origin. Now, it turns out it's also not closed under scalar multiplication, and it's not closed under addition either. But it's definitely not a vector space. All right, what about this? The set of polynomials with degree 3. We actually already did that one, but I'll write it down here too. The answer here is no. It's not closed under vector addition. But maybe I shouldn't just jump right ahead to say that. Because when we're talking about polynomials here, polynomials with degree 3, If you think about what they look like, they look like this: a t cubed plus bt squared plus ct plus d. So you could think of it like that. You could also rewrite this as a vector that's just a, b, c, d. So this is a four-dimensional vector space. Well, it's a four-dimensional vector, but they don't quite form a space because it's possible to add two of them together and get something with a degree smaller than 3. That's what I mean by not closed under vector addition. All right, this video is getting kind of long. Let's save the other examples for the next video.